Good afternoon, everyone. So my name's Anthony Makin. You probably saw me last session presenting for my colleague, Ali, but this time I'm presenting work that we've done as a team at Rowan University. My advisor was supposed to present this, Dr. Islam Anthoiny, but he couldn't make it here, so I'm here presenting this work on multifunctional, additively constructed wall system for housing and sheltering. So again, if you were here for the presentation earlier, you saw this slide. It's in all of our presentations, but we always like to emphasize how the construction industry has not changed from the 1950s in the left to now in the 21st century. So even though our technology has continued to improve, we still use the same method of building our formwork, casting inside of that. And so our goal at Rowan University is to find ways to implement our new technologies and change the way our construction industry operates for the better. So as we know, with conventional construction, you place your wooden formwork and your reinforcement inside and you cast inside of there. We've been doing that for forever. The next step is what we call hybrid construction, where you introduce 3D concrete printing in, and you see this with companies around the world where they're building houses out of this, where they print a concrete formwork, they place their reinforcement, and they cast inside of there. And while we don't think this is a bad approach, we don't think we're using 3D concrete printing to its fullest potential. So our next step is what we call additive construction, where we can optimize our structure and print the entire structure without the need for any formwork. So a presentation that was done by my colleague Jenna on Sunday was we're designing arch bridges for compression-only structures where we don't need to add any reinforcement in. We can print the entire structure without the need for any formwork. So at Rowan University, our team uses locally sourced materials within 20 miles of our campus to develop a mix suitable for additive construction. We use cementitious byproducts such as fly ash and silica fume, and we focus mainly on printability, extrudability, and the buildability of our material. So to define that, extrudability is the ability to eject the concrete mix through a printing nozzle without blockage or significant damage to the quality of the print. Buildability is the ability for the print to build up vertically layer by layer. So our material has to be able to provide stability as the load increases as we add more layers up. And we also need to have a long open time for our mix. If we have a very short open time, it's going to clog the nozzle. We won't be able to keep printing. If we have too long of an open time, the material isn't going to set as we build up. It won't be able to support the loads above it, and it'll collapse. We also deal with shrinkage. As we remove the formwork, we're exposing our concrete to air, so we do have shrinkage issues with our concrete as well. We do various tests for fresh and hardened properties at Rowan. I'll talk a little bit more about it later, but we do flow table and then setting time using a Vicat needle. We also do compression tests using 2-inch cubes. And then we also have at the bottom some pictures of good extrudability and buildability of our material. So you can see on the bottom left, we're able to print some complex geometries, and we have maintained good extrudability throughout the entire print. We're also able to print with good buildability. The picture on the bottom, while you can't see it, and I'll kind of talk about it more later, but in this picture we're printing a vase, so it's concaving outward as we're building up. The diameter is getting larger. Some other hardened properties we look at is the fusion of our layers. So we've tested some specimens, and you can see here, kind of difficult to see, but you can see this is a side view of one of our prints, and you can see the layers fuse together really well. And so we're actually in the process of doing more testing on the layer fusion and gathering data to ensure everything is fusing well enough so we don't have any issues with interlayer bonding. We also collaborate with another professor at Rowan University, Dr. Adriana Triez, to do LiDAR scanning. We can take that LiDAR scan and create a CAD model and compare it to what our original design we wanted it to look like and see if we have any deformations with our material. So we have 3 different printing systems at Rowan University. On the left-hand side, we have our tube system. This print right here is a cylinder that we printed very early on when I joined the program. We ended up filling this cylinder with water and left water in there for a month. We wanted to see if we had any leakage through the layers, and we found no leakage at the end of the month, only evaporation was where the water left. We had no leakage at the bottom because we sealed it, and then between the layers there was no leakage. The middle image is showing our auger system where we can continually feed material in. With this, we printed a much larger cylinder to show the capabilities of this material. And then the last one showing our pump system where we were able to print with various slopes of vase as I showed earlier. So moving on to the actual project, which is housing and shelters, I wanted to start with some background information first. So in 2023, natural disasters displaced more than 2.5 million Americans. And with that, we need to develop temporary and permanent sheltering for these displaced individuals. However, we can't just construct anything. There needs to be a certain amount of criteria hit to ensure these people will be safe in the shelters that they'll be living in. So existing research proposed some important criteria for temporary shelters, which includes the following. You can see up here on the left: durability, safety and privacy, reusability, transportability, rapid assembly, easiness to store, and then expandability and compactness. Each of these factors need to be addressed when we're designing temporary shelters. Here we have some existing shelters that we found in literature as well. That includes the Super Adobe Ecodome, the Future Shack, and U-Dome. Each of these shelters bring advantages and disadvantages, which, for example, the Ecodome is very safe and durable. However, like I said, they do have some criteria that is not met. For example, the Ecodome is not easily assembled and reusable. With the U-Dome, it might be very easy to assemble and reuse, but it might not be as durable as we need it to be. The Future Shack, again, there might be some privacy issues because it's made out of glass walls. You don't want to have a shelter made out of glass. You want to have privacy in your home. So we need to develop a newer temporary shelter that can address all of those previous criteria that we showed. That leads us to what our team at Rowan University designed, which is a multifunctional wall segment made out of hexagonal wall segments and insulative foam. So the wall segment in here is 4 feet tall with openings and battery-powered lighting. Of course, you wouldn't probably use hexagon lights, LED lights, but that's just showcasing the ability to put in lighting systems if you need to. We printed 2 wall segments and then connected them with a corner column unit. And then we believe that the multifunctional wall addresses all of the main criteria that I presented before. So going into more of the methodology behind designing our wall, the first step is, of course, taking our raw materials and developing a printable mortar, followed by material testing and ensuring its printability and strength. We then develop a 3D CAD model using CAD software such as Onshape, Fusion, SolidWorks, and then upload this 3D model to a slicing profile. In our case, we use Simplify 3D. With our printer settings imported, we're able to look and see, design our model and print it in a way that we want to print it to optimize the structure. The printer we use at Rowan University is a SCAR Elite Roadrunner, where we can print 20 feet long, 14 feet wide, and 7 feet tall. In this case, we print it with our tube system, which I showed before, which is the smallest that we have, a closed system where we have an 8mm nozzle. After printing our segmental pieces, the wall was assembled using silicone and insulative foam. So starting with our mix results, we tested 2-inch cubes, like I said, in compression, using excess material from before and after we printed. And so you can see in this table here, we have compressive strength data at 3, 7, and 28 days from before and after. We found that our compressive strength reaches almost 69 megapascals at 28 days. We also did flow table and Vicat needle setting time tests. With the flow table, we got around 114 millimeters with our material. For our Vicat needle, we targeted an initial setting time of around 1 hour and a final setting time of around 3 hours. Talking further about the CAD modeling and slicing, like I said, we developed 3D models using CAD softwares. We then take this 3D model and upload it to our slicing profile, Simplify 3D in this case, and we can generate a G-code based on off a printing path that we prefer. So what you can see here is we designed our 3 different designs you can see on the right-hand side. We basically have a singular line going around the perimeter of the print, and then we have double lines in the center to create the hexagonal shape, connecting everything together. And we're able to do this with a combination of our design that we make in a 3D model and also with the slicing setting profile that we upload from our printer that we have. For our wall segment, we designed 3 different pieces. So our first piece, which is shown on the bottom left, is just 3 hexagonal pieces printed simultaneously in one printing path, basically. The second segment, which is placed right above, you can see in the picture at the top, is the top right image. This one has 2 hexagons in the center and then 2 half hexagons on the end. Our third and final piece that we designed is our edge piece, so this will be the top and the bottom of our wall. This has 2 half segments in the middle and then 2 quarter segments on the corner. And so we designed it this way so we're able to print these segmentally, assemble them together, and they'll all fit together because the dimensions are, again, the way that's set up, you can see in the image, that's how we intended it for it to look. Along with developing the wall segment, we designed a corner column to connect the 2 walls together. The column was printed 4 feet high in its entirety in one printing session. So unlike the other specimens, which were printed segmentally and assembled together, this was printed, again, in one printing session where we just had to keep, every time we run out of material, pause the print, refill the tube, and reprint again. We have easier means of doing this now with our auger system that we have, but in the, before when we did this, we used our tube system, so it was a lot more of a hassle to switch everything out. Basically, these are octagonal pieces that have brackets on the end where we can use, we can connect the, we can use like straps to connect the walls to the column, and then again, the brackets can be moved along the octagon to create kind of angled connections too if we wanted to. So we can change the design depending on the needs. We also printed some, just the proof of concept, edge and interior connections. Again, these are the same design but adding an extra octagon along. And then like I said, we can try to change the bracket location to create angled connections as well so we can have angled walls. These were only printed a couple inches high just for proof of concept, but if we were designing a wall segment in the future, we could scale these up much larger. So the final step in our process is assembling everything together. So what we did is we assembled everything together using silicone, like I mentioned before, where we poured a thick layer in the openings between the segmental hexagonal pieces, which is shown in figure B. We then cut hexagonal foam for insulative purposes by using a hot wire, and we assembled this into the wall segment, which is shown in figures D and E. We then used clamps and U-bolts to connect the 2 wall segments and the column unit together to a wooden base, which is shown in figure H. The final assembly, like I said, is shown in figure H, where we also included battery-powered lighting and window openings to simulate a real wall segment. Of course, we understand that this assembly process would take too long to do ourselves. So if this project were to be scaled up, we would need to automate this process, of course. So our lab at Rowan University has access to robotic arms that we can assemble the wall on a production line, where we can program the robots to place the wall segments in their proper location, seal the gaps between the wall segments, cut insulative foam and place that inside the wall segments as well, and then seal the entire wall segment together. We believe the future of this project requires a production line. Again, it would be too difficult to have us sit there and manually do the labor every day. And this figure just envisages a future plan for the honeycomb wall assembly process. We also completed some experimental tests on the wall segment to verify its load carrying capacity. This was a much smaller wall, so this one's only 2 feet high, 2 feet long, 22 inches tall. And then we placed 2 columns at the end to restrain lateral movement during testing. So here we've shown the video of us testing it using an actuator in our lab. We tested this to gather load carrying capacity data, where we placed a spreader beam and hydrostone to distribute the loading from the actuator head across the entire wall segment. We didn't include the columnar units in the testing because we didn't want this to skew our data. We wanted to focus just on the wall itself. And the image, again, the video on the right is just showing the testing of this, which I'm just going to skip through. You can see the deformation in the wall before it eventually gives out in the end, right here. So we found the wall reached a maximum loading of around 10 millimeters at 18.6 kilonewtons. After reaching its maximum loading capacity, the wall experienced ductile failure, which we believe is due to the foam inside of it, as well as the silicone we use for the connection pieces. The wall eventually failed at 11 kilonewtons at a deformation of 47 millimeters before sliding out of the testing setup. We then compared the wall to common wooden stud walls, which 2x4 and 2x6 walls, to compare the load carrying capacity of conventional housing systems. So we found that our load carrying capacity was around 30.5 kilonewtons per meter. And so while the 2x6 with 12-inch spacing provided the largest capacity, around 35 kilonewtons per meter, our wall performed considerably better than every other stud wall that we compared it to. So we believe that with these results and then some continued improvements with our wall system, this innovative design can be used for temporary housing as well as a potential new wall system for permanent housing as well. The last thing I want to mention before I wrap this up is we did some further testing on our layer fusion. So we took our broken specimen, and you can see we wanted to make sure our layers were fused together well to make sure that's not the reason why this failed. So our goal is to ensure that the layer bonding is not the reason that we fail, which we believe in this case this was not the reason why. We also did LiDAR scanning of our assembled wall, and we're taking that data through a CAD model and comparing it to see if we had any deformation to compare the original model in our CAD software to what we ended up with, what our final result was. So before I wrap up the presentation, I wanted to promote our paper that we published on this project. If you're interested in learning more about the wall, you can find it here, or you can ask me any questions you want about that. I want to acknowledge that this work was made possible by the U.S. Department of Education, the GANT program, and then I want to thank you, and also I want to acknowledge my team at Rowan University. Without them, this wouldn't be possible. So my advisor, Dr. Montawi, my colleagues, Ali Ahmed, Jenna Malarino, Zaid Hanoun, and all the undergraduate students that we work with. Thank you very much, and I'll take questions if we have time.